Sometimes it's what can you subtract or difference. Okay, but these are all sequences, and as you guys could probably feel, especially in a computer field, isn't it more useful to have the explicit form rather than the implicit? Because it mirrors what type of data structure? Rhymes with array? Array, right? Because you can just index the number immediately, right? And in computer science, an array is one of the most powerful data structures that we have, okay? It can help you guys to sort things. It can help you guys to access things. It can help you encode things. You can do multi-dimensional arrays. So arrays are really cool data structures, okay? And basically, like, even like for those guys that remember what a struct is basically an array. That's all it is, okay? It's just a more formal type. So anyway, sorry about that. I'm trying to make some connections for those of you guys that are computers, like, why do I have to take math? I'm a computer science major sort of thing. So that's why. All right, anyway, more stuff. All right, now the difference between a sequence and a series, okay? Most people like say, oh, I know that there's a sequence and there's a series, but most people don't know the difference between the two. They're very similar, but they have one difference.
You add them.
You just basically add up the terms of the sequence to get a series, okay? For those of you guys that are in Calc 2, you study infinite series. What happens when you add up an infinite term, okay? So that's the difference between a sequence and a series, okay? And for those of you guys that are in your Calc 2 and you're studying series, eventually you'll determine whether it's convergent or divergent, or hopefully you will.
The radius of convergence.
Yep, and then sometimes for a power series,
Yeah.
there's only a specific domain of values
Yep.
to which that series is convergent
Convergent,
upon,
yeah.
okay? If you go outside of that, then it bifurcates, or it just diverges, it does weird stuff, okay? If any of you guys are interested in chaotic dynamics or fractal geometry, fractals can diverge if they're based on a power series as well. So there's a lot of applications for infinite series. Okay, I love series. They're like one of my favorite fields of study. But anyway, obviously, because you could never tell that by anybody. Okay. Guys, when we look at this, basically for a series, most of you guys have seen this before. There's a lower bound and an upper bound. And then this guy right here is the sequence. Okay, so basically all you do is you just plug in the numbers and then you just evaluate. Okay, these are really easy problems, not meant to be difficult. Okay, at least the first one. So if I had, and I wanted you guys to evaluate this series, okay, the series from I equals 2 to 6 of I squared. Guys, what does that mean for us to do? Somebody just, go ahead, Don.
All the things from 2 to 6 and you add them together.
All the integers, right, sir? Right. It's not because that's okay. And I just wanted to make sure that everybody knew, like when you said things specifically, and I knew you knew what it meant. Okay. So Donnie, would it be okay if I wrote it as 2 square plus 3 square plus 4 square plus 5 square plus 6 square, sir? Okay. That's all the integers between and inclusive of 6 and 2. Okay. At this point, guys, we just add it up, right? So this is a really easy problem. Okay. We just go through and add it. So we get 40, and then we get 25, so it's 65 and 25. Is it 70? Or 80? 80, sorry, I was getting there. I forgot to carry one. So that's just 80. Okay. So literally, guys, a sequence would just have commas. A series has the plus sign. So that's the difference between a sequence and a series, okay? All right, now, unfortunately, if you look at letter B and you try the same method, well, what happens if you do that? Yeah, you're just going to sit there for freaking ever doing the
Don't you have
problem.
that Gaussian method, like the first term, last term, divide by 2, then multiply the number of terms?
Well, that is true. There's a closed formula for an arithmetic sequence.
Okay.
But this is not arithmetic because it's squared. Arithmetic means, like, for instance, 3, 6, 9, 12, 15. They're separated by a common difference. So that's where you would use that formula. Okay? So don't try to overextend those, okay? It's good that you knew something, though. That's better than Congress. All right. So, like we said, guys, if we tried to do this by hand, we'd be here forever, right? We could use our calculators, but it says do it without a calculator, so that contradicts that. So here's my suggestion, guys. For something like this animal, maybe what we could do is just start listing out the terms and maybe see if something good happens. Let's hope it does, okay? So, let's just go ahead. I'm going to plug in 1, I'm going to plug in 2, I'm going to plug in 3. So if I plug in 1, this becomes 1 over 2 minus 1 over 1. Okay. Plus, I'm going to plug in 2, so that's 1 over 3 minus 1 over 2. Plus, so I'm going to plug in 3, I get 1 over 4 minus 1 over 3. Plus, I'm going to plug in 4, 1 over 5 minus 1 over 4. So all I'm doing there, guys, I'm just plugging in n equals I equals 1, I equals 2, I equals 3, I equals 4. Now that pattern would continue, right, guys? It would just keep going on indefinitely until we got up to maybe 100,000, or I'm sorry, 10,000.
10,000, yes.
So let's just go ahead and plug in 9999 and then 10,000. So this becomes 1 over 10,000 plus, or minus, excuse me, 1 over, or minus 1 over 9999. And then finally plus 1 over 10,001 minus 1 over 10,000. Okay. So all I did there, guys, was I just wrote out maybe the first 4 terms and then the last 2 terms. Okay, so let me give you guys a minute to copy that down, because there was a reason I did all that stuff, I promise. It's not just to torture you all.
We had the problem in Calc 2, I remember it.
Yeah, this is a very common type of problem that you guys might have seen in calculus too. Okay? And some of you guys are noticing what's going on here. So somebody tell me, guys, why did I write out maybe the first 4 or 5 terms of this?
To get a pattern, the negative, like half and half cancels out,
Because
1/3.
what we'll notice is that we have a positive half and a negative half, right, guys? So they go away. We have a positive third and a negative third. We have a positive fourth and a negative fourth. Guys, wouldn't the next term, even though we didn't write it out, wouldn't I have a positive fifth and a negative fifth, right? So these guys just all cancel out. In fact, doesn't the pattern continue at the very end, okay? Because I have a positive 1,000 or 1 over 10,000, a negative 1 over 10,000. This guy would cancel out too, wouldn't it? Because before that, in the previous term, there would be a positive 1 over 9,9999. Okay? Well, after all of that, don't I literally just have negative 1 from right here plus 1 over
10,001.
10,001, right, guys? And if I wanted to combine those, I'd get a common denominator. So I would get negative 10,001 over 10,001. Or in other words, this would just work out to be negative 10,000 over 10,001. Okay? Now, that very rarely works in real life, but of course we're in math life, so I can just make up problems that they do work. Okay? Maybe some of you guys have seen this before, it seems like, or you might have remembered it, but does anybody remember, that's a specific type of series. It either starts with an S or a C. Does anybody remember the name of it? What is it? Telescoping.
Telescoping.
That's all right. You know what? Alex Trebek will take that answer. Judges say good. Yeah, that's something called a telescoping series, where inside the terms cancel out. Okay. And this is one for those of you guys that are going to take Calc 2. You might have to build a telescoping series by doing partial fraction decomposition. Oh, lovely stuff, right? So this is something called telescoping. There's another name for it. It starts with a C. Sometimes it's called a collapsing series because, and obviously you can see that inside it just sort of it's going to self-contained implode. So telescoping or collapsing. Collapsing, yeah. Collapsing, yeah. I always call it telescoping because it sounds a lot cooler. So, all right. So guys, any questions? If I were to give you guys one of each of those on your homework, you guys would be able to do those to where you guys could just collapse the terms. I'll probably give you guys one like that on the exam as well. Okay, Adam, go ahead, sir.
I answered that A is supposed to be 90, not 80.
Okay, so this is going to be 40, and then this will be 25, and then so 40. I'm sorry, it's 40 and 25, and then 25 and 1. Yeah, you're right. It is 90. Usually when I can add correctly, but just write it on the teacher evaluation. Teacher cannot do simplistic addition.
Sorry, math,
Way beyond my abilities. Yeah, sorry about that.
Series, that's funny.
Yeah,
Yeah. Telescoping series.
I can prove if an infinite series is convergent or divergent, but if you ask me to do arithmetic, nah.
We're screwed.
Yeah, oh yeah. Boy. Alright. Other questions besides my inability to add whole numbers? Sorry, Adam. But at least you give me the bitch slap and put me in check. So I appreciate that. Alright. Another idea that I want to look at, that we're going to have to utilize when we do our proofs by induction, is something called a change of variable. Okay, these problems are actually really easy, okay? Like I said before, guys, it's always easier if you can write your series or your sequence in a simplistic form, okay? Now, sometimes what we can do is we can take a series that looks ugly, okay, like some of the ones that we have, and just change the index, okay? Maybe some of you guys have done this in computer science where you had an array and you basically just changed the place where it starts and you got a new array that was a little bit easier to work with. Maybe not. I don't know if you guys have done that or not, okay? But I just want to show you guys some examples of where we have a series and we just use a change of variable and then we go ahead and give it something a little more simplistic, okay? So, I have this first summation or series here. I equals 4 to 35 of I plus 3 over I squared. And I want to make the change of variable j equals I plus 3. Okay? Now, is it not true, guys, that if j equals I plus 3, I would have to be equal to what then, guys? J minus 3. Good. So we can just subtract 3 from both sides. Good. So this implicitly means that wherever I see an I can plug in j minus 3. Okay? So I replace j's with I plus 3. I replace i's with j minus 3. So let's just go ahead and substitute. Okay? So, I'm going to rewrite the series. So now instead of having an I for the lower bound, we have a j. Okay? Instead of going from 4 to 35, what should be the lower and upper bound respectively?
7 and 38.
Other way around. Oh, wait.
No?
No, you're right.
Yeah.
So we plug in 4 right here. You're right. I'm sorry, John. So we plug in 4 right here. So this would be 4 plus 3. And then for the upper bound, that would be 35 plus 3. Because we said that j equals I plus 3. Nice. Does that make sense to everybody, guys? We're just plugging in the lower and upper bounds back into our substitution. In the numerator, wherever I see an I, I'm going to replace that with j minus 3. So I would get j minus 3 plus 3 divided by quantity j plus 3, or sorry, j minus 3 squared. Okay. So really, guys, when we do a change of variable,
On the why did you do j minus 3 plus it? You can just write j, right?
oh yeah, I just want to make sure when people go home, they remember, how did it just become j? Where did the 3's go?
Okay, good.
Okay? So I'm just saying that wherever we see an I, we plug in a j minus 3. Okay?
Okay.
But yeah, we're going to simplify this. Okay, so Mr. W, you correctly identified the lower bound to be 7 and the upper bound to be 38. Okay. And then the numerator, j minus 3 plus 3 becomes j. The denominator just becomes j minus 3 squared. Okay, now, I don't know if that's any better looking than the previous, okay? But these two series mean the exact same thing, okay? Maybe for some reason you want the numerator to have one term because it's easier to work with, okay? So that's what we're doing with this. We're just rewriting it so that it's in a little bit easier or a different form to work with, okay? So does that make sense, guys? Any questions? Okay. The next one just as easy, okay? What I'm going to do is I'm going to start by solving for j, or sorry, for I. So it would be clear that j plus 10 is equal to I. So all we do is just add 10. Wherever I see an I, I'm going to replace that with j plus 10. Wherever I see a j, I'm going to replace that with I minus 10. Okay, so since I is equal to negative 9, I'm just going to plug negative 9 back in right here. Okay, so j is going to be equal to negative 9 minus 10 to n minus 10, and then we have to also include for the other minus 10. So all I'm doing, guys, is I'm taking this and I'm plugging it back into this I right here. Because remember, the lower and the upper bound are still representations of the index I. Okay? So this is going to be n minus 10 minus another 10. Does that make sense to everybody, guys? All we're doing is we're just plugging this back in. So we plug in the lower and the upper bounds back in there. And then for the rest of it, wherever I see an I, I'm going to plug in j plus 10. So this is j plus 10 minus 10 squared. J plus 10 minus 9 And by the way, you don't have to go through all of that. If you can just go right to the answer, that's fine. I just want to make sure that for those of you guys that haven't done your change of variable yet, with involving sequences and series, that this is how you guys might have to do it. Okay. For our answer, series j equals -19 to n minus 20. And then we just get j squared times j plus 1 quantity cubed. So any questions I can answer for you guys about what a change of variable is or how we might implement it? It's really just substitution, that's all it is. Okay. I might have asked this question before. I know some of you guys have taken differential equations. How many of you guys remember or had done that? Okay. What I remember is actually using this when you do the series solutions. Do you remember doing the series solutions, Don? It's like one of those things like, you don't want to remember as a child, like for me. There was an old show called Tic-Tac-Toe, and there would be like a dragon that comes up if you get 3 in a row, and I was terrified of that, and I was terrified of the vacuum. I felt like a cat when I was a kid, but so those are my memories as a kid. So that's why I ended up being a math teacher. So all of my fears I could instill upon you guys.
Yeah.
Yeah,
You had a wonderful childhood.
I did. I definitely did. Yeah. So I remember Tic-Tac-Toe. I was afraid of Wink Martindale. Seriously, like the worst game show host ever. All right, the next thing I want to look at this afternoon is I want to look at factorials, okay? A lot of you guys probably know what a factorial is, but if not, no big deal, they're fairly tame, okay? Whenever you see n exclamation point, that doesn't mean that n is happy or anything like that. In fact, n is just a factorial.
Do you have to scream and?
Yeah, it doesn't mean like scream it out or anything like that.
It's enthusiastic.
It's somewhat enthusiastic, yeah. Actually, it gets really big really quickly, so maybe it is enthusiastic. So whenever you see n factorial, that's just n times n minus